here is my slides. So if you can see the screen well, and I'll get started. So I wanted to spend today's like this 20, 30 minutes to talk about our recent work on how we can visualize ultra-fast photothermal dynamics using a new technique that we developed in the lab called decoupled optical force nanoscopy. And so I'm with the EC department, but also partially affiliated with the bioengineering department. So for those folks who are not familiar with the Midwest or UIUC, we are located in the central of Illinois and over here. And this is our campus. My lab is located in the north side of the campus and in a building called Micro and Nanotechnology Laboratory, where LED was developed. So here is my lab with graduate and undergrad students. Last year, we went for a summer kayak trip. And I want to acknowledge the students who actually did the work, and without their hard work, I won't be here today. So the majority of the work I presented today is done by Henry Wang, and also with Xiaodong Ye, who's also a PhD student, and Joshua Yu. And I wanted to also acknowledge my colleagues who collaborate with me in this work, Professor Kathy Murphy in the chemistry department, and Professor Yunxin Cheng in the EC department. So my lab and the bio-nanophotonics lab, we're mainly working on nanophotonics devices and instrumentation, but with a focus in applying these devices and instrumentation for biomedical problems. So primarily, we're doing wave engineering across different skills and space and length skills. And a technology we often use is called metasurfaces, and basically engineering the wavefront or the near field profiles. Using that, we actually establish tools such as this today's talk on optical force and nanoscopy imaging. So we're mainly imaging nanoscale light matter interactions. And we also have 2D surfaces, called metasurfaces, that we are engineering the near field or far field interactions, so we can create a more or other types of sensing mechanisms. And recently, we also started with working these large-scale metasurfaces for wearable devices. And so today's talk focused on the first topic in my lab. And in the light-induced interactions, especially here, we are interested in studying the light matter interactions at a single nanoparticle level, especially plasmonic particles. So when light is interacting with these plasmonic particles, and there is induced effect, and some of them associated with the stress or forces, some associated with the thermal effect, like the photothermal effect. And the photothermal effect has been a long-term associated with the plasmonic field, and this can be traced back to 2002, where Michael Orrid's group developed this first photothermal microscopy technique. And following that, actually, especially combined with plasmonics and using the photothermal effect, the group in Rice and Georgia Tech has worked on cancer therapy and basically generating heat and annihilating cancer tumor cells. And the photothermal effect has also been applied for nanoscale welding, basically using these shining light onto these nanowire junctions, then you can create weldings with very low loss at the intersections. And different groups in France also studied, the Voss group studied how to use nanoparticles and the photothermal effect with pulse light to generate bubbles and nanoscales. And following a few very significant work, I can only cite a few and apologize for those who I haven't cited in these slides, because the field is expanding dramatically, and the photothermal effect has been used across field from imaging, biomedical, and also particle synthesis, especially recently in energy storage. So in the field, there's also a discussion about all these interactions as being induced by the photo effect or photoelectrons or photothermal induced chemical reactions. So there has been growing numbers of studies, and also the review papers talking about what kind of effect actually associated with that. From my personal point of view, I think one of the challenges for studying in depth of these effects, or how to differentiate what kind of skills or associated with these reactions, maybe partially due to the fact that we don't have a tool that can study these interactions at a much finer spatial scales, and also at reasonable time scales. So along that directions, and we are interested in studying the nanoscale photothermal interactions. And to study photothermal interactions, there are kind of two directions you can consider. So one way is to go through like scanning probe techniques, where you can have a really fine spatial resolution. However, this kind of technology, like basically you rely on the probe scanning across nanoscale samples. And in a sense, you do have a really large, high spatial resolution in a nanometer regime, but you lose the temporal resolution due to scanning. And your scanner can be enhanced, for example, into kilohertz regime, so that still limited your time resolution into millisecond. On the other sense, you can also think about applying like electron beam type of technique, because here we are trying to study these photothermal processes in both high spatial and temporal resolution. And the electron beam microscopy technique can potentially provide high spatial and a high temporal resolution as well. And the limitation of this approach is like the study is in vacuum. So if you were to study these, especially the plasmonic particles, eventually we wanted to apply to biological environment, and we would like to study it in the environment that would be relevant. So the vacuum will limit this kind of application. So using scanning probe actually can potentially dissect or get the information about the photothermal effect, because scanning probe techniques mainly rely on the near field interactions of the forces. And on top of that, if you introduce light to it, and the light will generate associated force. So when the scanning probe is sensitive to forces, you're also capturing these nanoscale light matter interactions. For example, using these scanning optical force microscopy techniques, researchers in our field has actually studied various of nanoscale materials. For example, works in Belkin's group studied these monolayers molecules using these optical induced forces. And also Shiva's groups working on these nanostructures or studying these nanoscale interactions using the optical force, and basically integrating light excitation with the scanning probe as well. And also Naomi Hallis group and the recently in Vikram Mashinher's group in UC Irvine. So our group, when I was in Jen's lab, we worked on combining the inverted optical microscope on top with atomic force microscope. And then we can put nanoscale specimens in between. And here we were just mainly focusing on imaging the light-induced forces. And the work here a few years ago, what we studied is actually a special nanoscale structure. It's not a particle in this in a sense, but it's more like an inverted structure or an aperture. So a cartoon actually shows about this setup. From the bottom, you have circularly polarized light coming in, and then the light getting like actually enhanced with this coaxial aperture. And on the transmission side, we have an atomic force microscope, and we're measuring light-induced forces. In this case, we're especially pick up the light-induced forces that is sensitive to chirality or the handedness of the light. To do so, actually, we make a nanoscale chiral structure also on the AFM probe, and then scanning across it. And we can see actually when light was on and off, these forces are turned off. So confirming these forces are indeed coming from light. And also when we change the polarization of the light, you can see the force also changes sign that matches with our theory. But this actually study mainly focused on picking up the optical force associated with the handedness of the light, but didn't really study the thermal effect. So went along, we actually are more interested and found out that actually the optical force has a lot more richer information associated with that. So not only actually optical force can be related to the optical polarization or optical properties of the materials that we have studied, but it can also be associated with the thermal properties as well as acoustic properties. Well, on top of that, you can collect the structural information as a traditional atomic force microscope or AFM. So the challenges here is still we're actually limited by the scanning probe. So in the following, I'm going to show you how we can actually speed up the process without speeding up the mechanical scanning. And another challenge is this light-induced forces actually contain a lot more information. We recently realized that while we are doing this study, and the optical force, not only just the radiation pressure, optical gradient force, especially for plasmonic nanoparticles, these light matter interactions, also contain these photothermal force, because your measurement is built upon these near field interactions. If you have a pulse light, you can also create a stress onto the cantilever. This is called photoacoustic force. I think last week we have Li Hong's talk about photoacoustic microscopy. So a similar photoacoustic can be generated at the nanoscale as well. So all these forces actually are induced by light. If we were to study only photothermal force, and we actually need another technique to differentiate all these forces. However, they come from the same source. So it's inherently challenging to delineate. But if you look closer to all these three forces, although they are all induced by light, they essentially has a little bit different actually mechanisms when these forces are induced. For example, the optical gradient force, especially plasma nanoparticles, it's coming from these like polarized light and the dipole interactions between the probe and also the nanoparticle. And the photothermal force actually coming from the absorption of these plasma nanoparticles and then generating a photothermal expansion, and then that interacting with the AFM probe. And the photoacoustic force, on the other sense, coming from the pulsed light, right? If your light is pulsed, and with a certain time range of these pulses, you could generate a thermal expansion and then a contraction because the particle is going to cool down. And this expansion contraction will generate the propagating acoustic wave, and that interacting with the probe, both on the tip side and also on the cantilever. If you're looking at if you're modulating your optical pulse in a particular time domain, particular way. So here we are modulating with a square wave. This is quite essential because once you're modulating it with a square wave, okay, so the duration of this one was not doesn't need to be exact, right? So square wave, the exact duration here coming from our modulation frequency. But the important thing is when you have a square wave modulation, your optical gradient force would follow immediately. So here indicated by the cyan color. So because this optical gradient force on the plasmonic particle generate attractive force, so the time scale you can consider is instantaneous due to the time resolution we have in the electronics. So your optical gradient force will generate another kind of this even function. So if you're thinking about you have an even function in the frequency domain, and this even function has 180 degrees of phase difference compared to your excitation or your modulation laser. So if you analyze it in the frequency domain, you will find out this force should lie on the real axis, but on the negative side, So the second force, which is a photothermal force, has a slow actually heating up time. In this case, we analyze the time to be about 200-ish of nanosecond. And then it will get into equilibrium. And then as the pulse close, this is within one cycle. Of course, you have many of cycles of these laser pulses. And then it will cool down. So has a rising and cooling edge. If you analyze this pulse, okay, it actually can be considered as an even function and superimposed with a null function. So if you analyze this one from the time domain to the frequency domain, this should be a complex number. So it has both a real and an imaginary components. The last one is the photoacoustic force. Okay, so which actually coming from a second derivative of time, temperature over time. And if you think that way, it has a pulse at the rising edge and then coming down, and then another pulse at the like when it's cooled down. Okay, so that roughly is an odd function, and it should lie in a frequency domain in the imaginary like axis. So if we were to compose or convert our measurements into the frequency domain and extract the phase of these forces, and then we can actually redistribute the phase into these three different regimes. And we can assign these forces associated with these forces to these different origins. For example, if you find a force with the phase lying on the negative or real axis, that comes from the optical gradient force, and so on and so forth. So you can use the phase information to actually dissect and delineate what kind of forces it essentially coming from. So this is what we did, okay. So we come in with a laser, which is modulated with a square wave. And then we also actually can modulate your cantilever with this piezo signal. We particularly pick a piezo signal, and which is slightly different from the laser modulation. This is because we can actually also like decompose the topography information with the piezo modulation and also decompose them into this generalized, these three types of optical forces. Okay, so we study a plasmonic particle generally offered by Murphy's group. And these nanoparticles, you can see, is a very nice gold nanorod. And then we first measure it like a topography using the traditional AFM method. Then we turn on light and modulate it with the square wave. So we can extract the optical force amplitude and also the phases. Okay, so this phase here contain the phase from all these three types of optical forces: the optical gradient force, photothermal force, and a photoacoustic force. But if you look at these forces in detail, you'll find this force also has distributions. So here I zoom in into the edge of this gold nanorod. You find at the tip of the gold nanorod, this phase is about 180 degrees. So if you remember, that lies on the real axis, but on the negative regime. So that's associated with the photogradient force. And the background here actually is our photoacoustic force. I'll explain why it is a background. And then in the middle of the gold nanorod is actually this phase in between 0 and 90 degrees. So that's attributed to a photothermal force. So then we can actually pick up the background, which is uniform in this case, and then we pick up the photogradient force, which actually mainly focus on the edges of these gold nanoparticles associated with our understanding from plasmonic particles. The photogradient force is mainly enhanced in the edges. One is on resonance, and also the photothermal force, which is actually dominant on the body of these gold nanoparticles. Then we look closer into each of these forces. We find this photogradient force. You can actually dissect the information about the polarization of your light. For example, when it's off resonance, you will find the distribution of this photogradient force should change directions. So this is a simulation we predicted. And then when it's on resonance, with circularly polarized light, left and right will look similar. So then when we measure it and we extract the photogradient force from these three forces, we found indeed that this has matched our expectation. We also look into this photoacoustic force. And then here I wanted to just say a few words because this is a lot more details, I think. What is important about this photoacoustic force is for a nanoparticle like this size, depending on the pulse durations, you could have an anisotropic photoacoustic forces that you can map out. In this case, we're using a much longer pulses. So basically it's interacting with the entire cantilever. So that's why it's a background force. But theoretically, you could actually have a distribution of the photoacoustic force as well. So there's a lot of technical details. If you're interested in, please go to read this paper. And a few words about this one is that basically in the near field, it is not a spherical wave. Okay, so the take-home messages is you can have a different decays of this photoacoustic amplitude away from the gold nanoparticles. And assuming you can actually measure and imaging this photoacoustic force distributions or using the force microscopy technique to map out the photoacoustic distributions. What you will find actually on the long edges of this one, and so it decays, which actually starting this calculation also, this is a calculation of our numerical study and also analytical study, shows from the beginning of the edge of these particles. Okay, so the decay actually as a function of distance to the nanorod surface is different when you have from the long edge and the short edges. So the transverse direction and also longitudinal direction is different. It also is different in the near field from the spherical waves. So if you're in the far field, you may actually simplify these photoacoustic waves as spherical waves. However, in the near field, these are not spherical waves because as you go closer within, like, for example, in this region, like 20 nanometers, your like spherical applications and also the Green's function applications started to dissociate. And that's because the size of the particle and also a certain pulse of this particle and this near field interactions have started to become more prominent. Okay, we analyze with different like pulse durations here, some of the pulse being rather short compared to applications right now people have been using, but this is just to give you an idea, like there might be a way that you can optimize the pulse durations and to amplify the photoacoustic forces further, or the photoacoustic amplitude further. So there is a sweet spot that you can actually tweak the laser pulse durations, so you can create either the most anisotropy distributions of your photoacoustic distribution, or create a larger amplitude and or faster decay compared to the traditional far field analysis. Okay, so what we have seen in this case actually is this type of interaction. Okay, so this is a traditional photoacoustic pressure, and that was analyzed actually having these gold nanoparticles in these calculations. So we come in with this AFM probe, and then we're actually including all these elements in our calculations. And we find actually, as a function of time passed by, these photoacoustic force actually coming in and propagate started to interacting with the probe and also starting to interacting with the cantilever. And if we were able to summarize or looking at a larger scale, this is not a uniform force at this time scale. So again, our pulse is much longer compared to the numerical study I just showed. And this is hundreds of nanoseconds for the photoacoustic like pulses here. So that's why you see rather uniform, because if you consider the size of the cantilever and consider the time scale and also the speed of acoustic waves, and these interactions will happen in the entire cantilever. If you zoom out to a larger scale, this would be what you image for the exact photoacoustic forces using cantilever. So you will see a gradient over the distances. But we are imaging with much smaller field of view. So here you're seeing the photoacoustic force being rather uniform. And then we can also analyze it in the time domain. You can see this is very similar to our theoretical applications. Numerically, you can also estimate how big these forces are associated with that. And I wanted to point out these two peaks when they're measured with the cantilever, that actually associated with the force actually, or the photoacoustic pressure interacting with the front end of the cantilever and later on with the back end of the cantilever. So you see these peaks pulsing, and one from the forward propagation, the other one from the extraction. Okay, so lastly, I wanted to show you when we actually dissect and delineate this photothermal force, what it really looks like, and also how it actually evolved with a function of time that I promised to have a faster time scale. So if you think about what we have done so far, right, we actually dissociate these optical forces into the frequency domain by using the phase information to assign what kind of force or what kind of mechanism it's really coming from. Okay, so you find out the photo gradient force, the photo acoustic force, but then the other one on the complex domain is actually the photothermal force. If we were able to actually tweak the phase a little bit with a really fine scales, essentially it's as if we are looking at the photothermal propagation in a time domain. So there is a little bit of analysis about where this force is coming from, and this rather complex, but the takeaway is this force can be modulated by the optical frequency of how you're like modulating your cantilever light, and also the dithering frequency, how you're dithering your cantilever. And also it's related to how you're engaging your probe, because this is a near field interaction. With that, as a guideline, actually, we found out we can actually create this kind of mode during our force measurement. So in theory, this mode exists where like the color map is amplitude on the left, and the color map on the right is the phase of the force. Okay, so on the x-axis is how the dithering frequency away from the resonance frequency of the cantilever. And on the y-axis is how the optical modulation frequency is different from the natural frequency of the cantilever. You will find actually you only want the optical frequency and then also the dithering frequency here. I mean the optical modulation frequency, not the actual wavelength. The modulation frequency and the dithering frequency to be rather close. But what you can do is you wanted to find the amplitude of the force you're measuring roughly stay at a high amplitude, but then you can actually tune the phase across a larger range. So the reason you're doing this is by keeping the optical force amplitude as a high value, you have a high signal to noise ratio. And then if you're changing, for example, in this case, you want to fix the modulation frequency of the light, but actually change the dithering frequency, then you can sample all the different phases. So we did this calibration of our system. We found out indeed with the lower branch, you can maintain the higher amplitude. So this lower branch is what we are going to aim at, right? And then we wanted to actually change the dithering frequency by a few hundreds of hertz. Okay, by doing so, and then you can see you can actually vary the measured phases actually across a large range as if we're moving this bar. Okay, so you can sample different time. So this is what we did, and then we wanted to see how the photothermal effects start and end during the whole one duration of the light modulation. So this is a simulation we predicted when the light coming in, and this is a gold nanoparticle. If during the heating phase, you should see the gold particle is heating up, while all the heat is actually still confined or roughly confined in a particle without propagating out to it. During the cooling phase, of course, this is just a snapshot, and then your particle is going to cool down first, and then most of the heat is going to propagate to the substrate. In this case, we have a PMMA substrate, so the particle will cool preferentially, or the heat propagates into the PMMA substrate, then going to the air. Okay, so this is a one, actually, during one duration of the pulse is on. Okay, so the light pulse has about 1.5 microsecond. Okay, so because we modulating in hundreds kilohertz, and then so it's a square wave modulation, and we expect the temperature, and this is calculated temperature to rise, okay, in the first part, and then cooling down at the end. Okay, so we started with during the heating phase. So this is our simulated results, and bottom is our experimental result of mainly the photothermal force. Okay. So as it's heating up, approximately 100 nanosecond into the time scale, you can see the gold particle get heated up, but not the environment or the background. Okay, so then gradually heating up, you should expect the gold particles getting more like hot. So keep in mind the color map here is the forces, or especially the photothermal force. Okay, and then as you going through the equilibrium, so the center part gets more higher value, and then gradually you can see the heat propagate outside into the environment. And then during the cooling phase, you should expect the particle will get darker because it cooled down first, and then your environment is going to be hotter, right? So this is what we see. So the particle gets darker and the environment get hotter. So you start to see the contrast now associated with the cooling phase. And then as the particle completely cooled down and getting close to the room temperature, you can see there's no contrast between your particle and also the environment. So with that, actually, I wanted to summarize the talk, and hopefully I didn't, I go a little bit over time. And then today I showed you we can actually use this so-called optical force nanoscopy to actually dissociate different optical forces by using the phase information. So you can actually analyze what is the photogradient force, photothermal force, and the photoacoustic force. And by actually changing the phase information or picking up the right phase information, you can actually observe the heating and cooling stage of a single gold nanoparticle over a time scale. It's about a few hundreds of nanoseconds. With that, I wanted to thank, this is again my group is working on, and I want to thank my group and also my funding agencies. And I want to thank you for your attention. Now I'm ready to take on questions.
Yes, thank you very much for the very interesting talk. So we have probably time for one or two questions. There's the first one by Michelle already. Please.
Yes, thank you very much for a very interesting talk. I'm not familiar with this, but I had a question about the photoacoustic force, because I'm not sure I understand the mechanism of this force. So, in principle, I mean, you were mentioning near field, and so I calculate the wavelength of the acoustic wave. It's very, very large compared to your size, right?
Mm-hmm.
So, yeah. I mean, is it? I mean, is the name right? Because, photoacoustic, I see these acoustic tweezers, I mean, you manipulate objects at distances which are large compared to wavelengths. And here you're looking at the really deep near field, right? You are really at distances. So it's rather, to me, it's rather more like a sort of static, like, in optics, you have near field, which is like electrostatics. So for me, it looks like more, fluid dynamics, right? I mean, that is what is the origin of the acoustic force? It's a sort of pressure variation.
So, yeah.
And
so
this pressure variation is exerted on the whole of the tip, right? The whole tip acts as a receiver for this pressure wave.
Yep.
So is that correct? I mean, is that the way you calculate the acoustic force? I'm not sure to understand how you do your simulation.
Yeah, so in a simulation, actually, if you think about in this case, we estimated mainly is about what is your pulse duration, right? So for our case, the heating and cooling generate this pulse is actually about a few hundreds of nanoseconds. So if you multiply that by the acoustic wavelength, not wavelength, acoustic speed, right? We did it in air, so let's say 300, and then you calculate that's in a range about hundreds of micrometer. So about that's the kind of wavelength. Yeah, that's wavelength scales that we're looking at. So that's why we didn't.
I mean, can you say that just the tip of the probe is feeding the force, or the whole probe?
No, the entire
whole probe. Yeah. Okay.
Yeah, the entire probe, because that's why we did the simulation over time, right? So at the beginning, as that's the wave just propagate to it interacting with the tip of it. But during the whole pulse, actually, it's actually already the time scale. It's interacting with the entire cantilever.
Okay.
So you will see, if you were to see like a much finer time scale, you should see a pulse going up and a pulse going down. Okay, but what we see is actually the whole interactions with the entire cantilever.
Okay, it's clear. I understand now. Thank you very much.
Yeah, thank you.
Thank you.